Okay. We have a question of, can we look at some triple integrals? And especially converting from one system to another. So I'm going to do one of the most fundamental things you can do, which is the volume of a sphere. Okay. And just look at how we would change the coordinates. Okay. Um, Now we did skip the section on the Jacobian and how to use that, but and much probably be able to do in terms of that, but just because of college closings and so forth, we're just a little short on time. Okay, so okay, which is 256 thirds pi. So that's it. Um, this, of course, is your volume measurement in spherical coordinates. And we could picture that and so forth, but we've got 2 days to review. So if you understand the picture and can draw this thing, it's very good. If you can't, sure you remember it and have some understanding of why it is. Um, so if you were given this integral and asked to convert it to cylindrical or rectangular coordinates, okay? Well, you know your regions. Beta goes from 0 to 2 pi, and phi goes from 0 to pi. Okay. Now rho equals r squared plus z squared. So you say you go from 0 to 4, r squared plus z squared. You can do it with just inequalities, or you can do a picture. Okay. Cylindrical coordinates. It should be less than 5. So we could say this. Now, r squared plus z squared plus 4 means This is just a circle of radius 4. Okay. So we can say that so just to picture this, we have a circle of radius 4 r going this way, z going this way. So if we take a given value of r, I'll just say r equals r asterisk. Then we can draw this picture, which hopefully everybody's drawn a number of times. Using the Pythagorean theorem, we see that should be r star squared. Did z to go from negative to the square root of 4 minus r star squared simply because this triangle here has radius 4, and this is r. So that this leg is square root of 4 minus r squared. Okay, and that should be, hopefully that's pretty obvious. And then we have zero less than or equal to theta less than 2 pi, and there's a description in cylindrical coordinates, r, theta, and z. Cylindrical coordinates. Kind of squeeze it in here. But theta is going to go from 0 to 2 pi. 0 to 4. And z is going to go from negative square root of r squared. Okay. And then your basic area increment, as we've drawn out and everything, and as I hope you understand, is dr by r d theta. No, I'll sketch that as we're reviewing. So if this is a delta theta, this is delta R, then whatever sample point you choose within this increment, the arc length here is R star delta theta. This is delta R. So what you have is an approximate rectangle. This delta R by R star delta theta in the area is then approximately R star delta theta delta R. When you take the limit by a process that shouldn't be totally mysterious at this point, even if it is, note the similarity between this and this. Taking the limit as everything approaches zero, your delta theta and your delta R. So that the R star that you chose makes no difference. The delta R is so small, becomes so small that the dimension here and the dimension here don't differ by very much, nor does that dimension differ very much from the arc length. This is really, R star delta theta is an arc length here at some point within your increment. Okay, so here we've taken this integral in rectangular, in polar, I'll get it right, yeah, in spherical coordinates. And this is not the only way to do it, but we can translate these inequalities into cylindrical quantities. It turns out that we don't need to use this inequality on the using the arc tangent, because that's implicit in what we did over here. Picture. Okay. The side is basically a tangent of phi. Phi is measured from the z-axis. And this side is tangent of phi that goes all the way from the positive z-axis. Okay. Yeah. Okay. Very good. Very good. Okay. Um. Now, again, our alternative is to understand that that's a sphere of radius 4, because that's not necessarily given. Okay. You know, the question was how do you convert from one coordinate system to another? Now, if we have some function in here, some function of rho theta phi, well, become a function of r theta. Okay. Where r is rho sine theta, so forth. I'll do an example. So, and now, rectangular. And let's just go from so this means Stop and think, but it's like in the picture, this, there you go. X, Y, you got a point here, you got the Y coordinate, you got the X coordinate, here's the Y, here's your X, and here's the argument, opposite orientation. Okay, I just wanted to make sure I was writing that down. You could write this piece down. And then you could say, okay, well, this one tells me that, we'll let X go from down to four. Um, and then I can choose any one of these. I usually don't do this. Okay, let's see. Okay, then I did something like wrong here. I didn't square my four. Okay, square this and add it to this. Where? Yeah, never mind. I have more of those days. Okay. Um, you saw usually what this goes to many. And then you would have this in your picture. Let's just take probably been better choosing X here because it would look better to you than the spit so out there. Um, yes. Um, I'm gonna switch to just give a picture of the city. Um, the point is, if we got a Z star here, then by the same kind of picture we had previously, inside of the inequality. If this is Z star, and the radius of this thing is 4, then each of these has magnitude square root of 4 minus Z squared, right? So this picture leads you to this, well, to the inequality, x squared plus y squared less than or equal to square root of 4 minus Z squared. I think that's all no. Okay. Then in the xy plane, I should have written this out right. I got square roots here and not here, and I just don't want square roots there. Second thought I do, but let's write it out. Whatever. Got to correct something. Okay, clearly, and should be clear, but I don't know. That was some sort of brain fog today, the last few days. But anyhow, um, this should be the square root of 16 minus r squared here because this squared plus this squared has to equal this, right? Square this, you get 16 minus r squared. You get r squared. That should equal 4 squared. It's like a squared. B squared equals c squared. So replacing 16s. And it all goes back to what I wrote here. R squared plus z squared is rho squared. So rho Square should go from 0 to 6. Now, again, the way you would really probably do this is create the picture and work within the geometry of the sphere. In any case, we come over here and these floors should be 16s. The same reason those are. Okay. Now, this is just the radius of a circle of radius 4 in the XY plane, right? That's our radius square root of 16 minus x squared. Let's say x squared of 16, square root of 16 minus r. In this circle, you pick some sample value of x equals x bar. Triangles here. Y equals the square root of 16 minus r squared minus x star squared. Okay. Again, because this side is 16 minus r squared. This side is x star. That side's what you need to complete the Pythagorean theorem. Okay. Be a little more rigorous. Getting more stuff wrong is right. This is z star. So it's ought to be 16 minus z star squared, not 16 minus r squared. It's ought to be z star. No, really. Got to really apologize because that's got to be a little bit confusing. But where we are, we've got this result here. 0 less or equal to rho less or equal to 4. And then we can just take this inequality here, which really defines the whole thing, and say that z goes from -4 to 4. Illustrate that with a circle of radius 4. Upside down, because those aren't right. Okay, radius is 4. Pick a Z star. And get this triangle. I'm just going to do one triangle. This triangle, we have 4 here. We have Z star for this leg. So this leg is square root of 4 minus 16 minus Z star squared. So drawing the triangle a little bigger. Z star 16 minus Z star squared, which is what I used in my inequality there. But the picture was wrong. I have the triangle up here, and it's not where you want it. Obviously, can't directly apply Pythagorean theorem to that. And I have this leg labeled as form, which is absurd. Okay. Then, of course, we have the same triangle down here. Z is negative Z star. And of course, the legs of the triangle would still be Z star and R, assuming Z star is positive. Okay. So the point then is that this alone tells us that in plane, that we label the axis this time, this is the x squared plus y squared axis, okay? Or an R axis. So you have full circle of radius 4. Then for given radius, for given x squared plus y squared, you have a circle. This describes a circle of radius 16 minus z squared, z star squared. And then this follows. But we get that y is going to go from negative this up to this. So there's nothing wrong with these inequalities. They're the same. Had I chosen a y star, I would have gotten these. Is that clear? Want me to draw it out a little bigger? So again, this allows us to consider circle in the x squared, in the z versus x squared plus y squared system. And that's like the projection of the sphere into the plane z versus x. We could usually, if we have a sphere, we'll think of projecting it into the xy plane. Okay. In which case, this would be x and y let me do that picture. So now the drawn sphere. But down here in the XY plane, circle squared plus y squared equals r squared, whatever r happens to be. In this case, it's sphere of radius now you have a point on the sphere that lies above some point in the XY plane. If you got x star, y star for the coordinates of this point, then the coordinates of this point, well, you have the radial line of the origin to the point on the sphere. This leg is square root of x squared plus y squared. This leg is r. So if you draw this triangle out here, this squared plus this squared has to equal this squared. This is 16. Okay. So that this thing has to be 4 squared minus this squared. And you end up with the same inequality. If you were integrating the function, the f of r cosine theta r times sine theta c. Theta rho sine phi sine theta is rho cosine phi. Sense? This is take 2xy squared minus 5yz. Tangent wrong. Okay, error. I should have written out. And f of r theta c is going to be 2 cosine theta sine squared theta minus 5 sine theta. See, that makes sense. He's replacing x by the cylindrical coordinates in expression. So you got the coordinates up, so you got 2, and yeah. That'll be summary. F of r theta z would be 2 times r cosine theta times the square of r sine theta minus 5 times r sine theta times z, which is 2r cubed cosine theta sine cubed theta minus 5r sine theta times z. And of course, we could then factor out r sine theta. And if we wanted to integrate that, well, it's easy to do. Cosine theta sine squared theta, we just let u equal sine theta. We get u squared du. And the r is a simple polynomial, z is just integrate. Okay. And then I'll write out the result. Pay attention. F of rho and if r would be 2. Okay, the X and the Y would both have a rho sine theta on it. Okay. So your X, Y squared would both have a cosine. X would have a cosine of theta. Y would have a sine of theta, giving us 9 squared theta. When we factor out the rho sine theta for both. And then that's minus 5. It's sine phi, not sine theta. Then we have negative 5 rho sine phi sine theta times z. That not times z anymore. Times rho cosine phi. That's going to be 2 rho squared. That'd be rho cubed. Again, why is it rho cubed sine cubed theta? Because we've got x, which has a rho sine theta. We've got y squared, which will have the square of a rho sine theta. Not carefully, it's just straightforward. So if we were trying to integrate this function over the sphere, insert this expression in this interval, we would insert this expression in the cylindrical coordinate interval. Yeah, I wrote it up. We'd insert it here. And in any case, it's fairly easy to do. Okay. Then we would then we would insert this, there it is, into the rectangular interval that I never did write out. Thing. Thing I'll point out is that this might be the easiest one to actually integrate, because it's a sphere, among other things. And even though this function, rho, f of rho theta phi, is more complicated than this simple polynomial, you don't have to back substitute in anything with a square root in it. Okay. All you're integrating is cosines and sines. It works with sine squared that's accompanied by a cosine. And we've actually got a sine cubed. It can be written as a sine times 1 minus cosine squared. That then lends itself to simple enough substitution. Okay. So this integral would be easier probably than this one. You integrate r, you're going to get r squared over. First integrate with respect to z, you're going to get r times 2 square root of 16 minus r squared, which is not difficult because you got the r out in front, you do a u substitution. Then you integrate from 0 to something I erased and did replace here, but it should have still been full. So this one actually turns out to be fairly easy to integrate. If you integrate this one, you might end up with an expression that's a little more complicated to integrate. It'd be worth doing those as an exercise. Make sense? The other thing is, of course, now this gives you the volume of the sphere, that gives you the volume of the sphere, and this gives you the volume of the sphere. And the details are pretty straightforward to work out. You integrate with respect to y, you're going to substitute this. So now you got to integrate square root of 16 minus x squared minus y squared with respect to x. And that's where you probably get a little bit tricky. Because you'd have to use a substitution like y equals square root of 16 minus x squared tangent of theta, or something like that. Okay. So, try to put application by using coordinate system that fits the shape best. Okay. So you can express any interval in one coordinate system in terms of the other. Sometimes it's pretty awkward. Taking these inequalities and translating them here isn't too bad because you don't really have to use this one or this one. Okay. Sometimes. So let's just look at another example. This would be the paraboloid above the XY plane. Picture fairly simple to draw, so I'll probably screw it up, but let's see. Down here on the plane, a circle. It's 3. Up here, B equals 3. If R equals 0, that means you're above the origin of the XY plane. So that Z would be plus or minus the square root of 9 minus R squared. You would disregard the negative square root of 9 minus R squared because the area of this paraboloid of Z is positive 9 minus R squared. And it's automatically above the XY plane. Okay. In any case, you get a parabola up there. If you confine yourself to the RZ plane for any R, you get Z squared equals 9 minus Z. I don't know what's going on. It's going to be 9 minus R squared. What I was describing with that square root would be the upper half of the sphere, the hemisphere. Okay, so anyhow, now you got the paraboloid, the parabola. Down along the parabola. And you got this kind of a parabolic dome. Let's say we want to integrate f of r theta equals r cosine of 2 theta. Again, 3 variables to integrate it within this parabola. Cosine theta times z squared. Parabola would be z equals 9 minus r squared. The area above the paraboloid would be z less or equal to 9 minus r squared. So the integral zero to 3 with respect to r, 0 to 2 pi with respect to theta. And 0 to 9 minus r squared. Z. Again, it's a two dimensions, but your increment in cylindrical coordinates is r dr d theta down here, then a dz up here. Get a little approximate cube of dimensions r d theta by dr by dz. And then we got to fit our function in here. Got to write it. Z squared r dz d theta dr. I had dr d theta before, but I might r up here. So the order now is correct. And that's going to be a fairly straightforward interval. Going to integrate z squared will get z cubed over 3. So you're going to get a cube of this, which is going to be a polynomial in r. And you're going to multiply that by r squared. This is the r here, the r here. But it's just going to be a polynomial in r. It's going to be straightforward interval. Okay, we're in short times. We could describe this in rectangular coordinates very easily. R cosine theta is just x. So r cosine theta z squared would be x z squared. Straightforward x from 0 to 3. X. Z goes from 0 up to what I just wrote. So there can be no great mystery about this. We already know that in the xy plane, this thing sits on a circle of radius 3, which can be described by x going from -3 to 3, y square root of 9 minus x squared to the square root of 9 minus x squared. Then z goes from the xy plane up to 9 minus r squared, which becomes 9 minus x squared, which is r squared. And we get the principal integral of x z squared so z will go right here. square y. We'll go from square root of 9 minus negative square root of 9 minus x squared. And I might as well. Let's talk about proving the right limits. And there's the integral. From the z squared, you're going to get the cube of this mess. From the y integral, you're going to get these square roots of 9 minus x squared. So this integrate might be simpler than this one. It'd be useful.